All right. So let's get started. We have been looking into MOSFET-based circuits. So we till now we have looked into how MOSFETs behave, different kinds of amplifiers, which are common source, common gate, and common drain amplifiers. Those are the things that you have looked at. Now, using these MOSFETs, what else can we do? Right. So that's what we have been looking into from last lecture. We have looked into multi-stage amplifiers, that if you have multiple of those stages, common source, common gate, common drain, and arrange them in different fashion so that you can get, let's say, more gain out of the system, because you eventually cascade amplifiers. So that's what we looked at in the last lecture. We also started looking into current mirrors, because in the example problem that we were solving in the last lecture, you saw that there were three current sources. And that's basically your homework number 6, that when you try to solve that problem, you'll see that there are 3 DC current sources in that circuit. Now, it's never you can always use 3 different DC current sources in an actual circuit when you're testing it out in the lab, but then that's kind of cumbersome. It's a complex setup. You need to make sure that all 3 current sources have the exact values that you want. There could be variations, there could be mismatch. If you want to avoid all of that, you probably want to create those current sources inside your circuit, and it is possible to do so. So using MOSFETs, if you're using this kind of a configuration, that you have your I1, that's the original input current, that is going into a diode-connected MOSFET. We already discussed why do we call this a diode-connected MOSFET, because current can only flow in one direction if the gate and drain of the MOSFET is connected together, right? Because if current flows in the other direction, the drain terminal becomes the source terminal, and then by definition or physically your gate and source becomes connected, which makes the transistor off. And that is the reason why current can only flow in this direction, and that's why we call this a diode connected transistor. And then if you connect the gate of that diode connected transistor to the gate of another transistor over here, which is M2, the current flowing through M2 will be a function of the current flowing through M1. Now, we're going to prove that in today's lecture in detail. So our assumption would be the threshold voltages of the 2 transistors are equal. So VT2 is equal to VT1, equal to, let's say, VT. We'll also assume that the process transconductances, that is mu times COX of the 2 transistors, are equal. So K1 prime is equal to K2 prime. We also discussed in the last lecture that if M1 transistor is diode connected, then why is it automatically in the active region all the time? So if any transistor is diode connected, that is automatically in the active or in the saturation region. And that's simply because the equation for saturation or active is that your VDS needs to be greater than V overdrive. Now, by definition, or by this physical connection of the gate and drain being connected together, you can write VDS equal to VGS for the diode connected transistor, because drain and gate terminals are shorted together. And if you expand V overdrive is nothing but VGS minus VT. Now for an NMOS, this is always true. VGS is always going to be greater than VGS minus something when all the quantities are positive. And that is the reason why the diode connected MOSFET is automatically always in the active region. So if you see a diode connected MOSFET, don't even need to analyze. It will always be in the active region. Okay, so with those assumptions, what we can write is that your VGS2 is equal to VGS1. Why? Because the gate and source of both the transistors are connected together. The gates are connected together. The sources are both connected to ground, which means they are also connected together. So the VGSs are equal. Now, V overdrive is equal to VGS minus VT. If VT is equal, that is again another assumption. If VT is equal, then the V overdrive has to be equal for both the transistors. Because VGS is equal, VT is equal, so VGS minus VT has to be equal for both the transistors. Okay. All right. Now, if your M2 transistor is in active region, so if your VDS2 is greater than V overdrive 2, that's again an assumption. You might need to check it in a real circuit, that whether your M2 transistor is really in the active region or not. Or you need to make sure that you connect a VDS2 that makes the M2 transistor in the active region. That means VDS2 greater than V overdrive of 2. So again, with that assumption, you can write down I2, that is the current flowing through the M2 transistor, that is I2, equal to K over 2 times V overdrive square. So you have K2 over 2 times V overdrive 2 squared, because we are always talking about the second transistor. The subscript 2 means we are talking about the second transistor, the right-hand side one. Now, because V overdrive of 2 is equal to V overdrive of 1, the overdrives of both the transistors are equal, you can write K2 over 2 V overdrive 2 squared as K2 over 2 times V overdrive of 1 squared. And then you can write V overdrive as square root of twice I1, twice I over K. Right? Again, a formula that you have already learned and have already used in your homework number 4. So V overdrive is square root of 2 times I divided by K. And just remember to use the formula correctly, because in the homework problem, I saw some of you had used V overdrive as 2 times square root of I over K. That is not correct. Right? So this 2 has to be inside the square. Again, just think about the fact that VOV is K or GM is equal to K times VOV. From there, you can actually calculate this. Or I2 is equal to K over 2 times V overdrive square. From there also you can calculate this. So this is not correct. Some of you have used this formula for some reason in the homework while you are solving the homework problems. But make sure that you use the correct formula for V overdrive, which is square root of twice I over K. And again, this is just coming from the very fact that I2 is equal to K over 2 times V overdrive of squared. If 2 is outside of the square root, then I2 should have been K2 over 4 times V overdrive of squared, which is not the case. All right. So you have represented your V overdrive as square root of twice I over K. And of course, this is V overdrive of 1, so you're writing I1 and K1. So this becomes K2 over 2 times twice I1 over K1, because you are just squaring the square root term, because you had V overdrive of 1 squared over here. So that means you have K2 over K1 times I1. So this is a very interesting relation, that I2 is equal to K2 over K1 times I1. Now, what is K2? K2 is K prime, or what is K? K is equal to K prime times W over L. K prime times W over L. And K prime is nothing but mu times COX. So K is equal to mu times COX times W over L. Now, mu times COX for the transistors, both the transistors are equal. That's an assumption. So we made this assumption over here. So that's why K2 over K1 is just going to be omega, or W over L of 2 divided by W over L of 1 times I1. Okay. Now, if your lengths are equal, of course, you can have different lengths for the transistor. That will give you another degree of freedom, or that will give you another, let's say, design parameter or a design variable. But let's just say you are assuming that your lengths are always equal for the transistors. Then in that case, I2 over I1 is just going to be a ratio of W2 over W1. Whatever is the width ratio for the two transistors, the ratio of the currents will be exactly the same. So if your widths are equal for the two transistors, and of course the lengths are assumed to be equal, so usually you let L1 equal to L2. In that case, your I2 over I1 is going to be W2 over W1. That is the ratio of the widths. If widths are equal, the currents will be equal. If the width of transistor M2 is 10 times higher than the width of transistor M1, the current I2 will be 10 times higher than I1. So you have a very nice way of copying the current. So you are copying the current I1. So it's just a copy of current I1 that you have at I2. And it's not only a copy, you can have multiples of that copy. You can have 1 times of I2, you can have 2 times of I2, you can have 10 times of I2, you can have 100 times of I2. It's just that your W2 needs to be that much higher than W1. That's it. So if you have one current source, you can generate multiple current sources from that. All right. Now, this is just an example of how you're going to implement a particular ratio. So, for example, on the left side, what you see is that this current source, original current source I1, that is going into this diode connected transistor over here. Now, what's interesting is that instead of one diode connected transistor, you have two of them, but they are connected in parallel. So their drains are connected together, their gates are connected together, and their sources are connected together. So if all of the terminals are connected together, it's basically a parallel combination, right? So if you have a resistor and if you connect two resistors together, it's a parallel combination. Similarly, if you have two MOSFETs and connect all the terminals together, that becomes a parallel combination of the two MOSFETs. Now, just like when you have a parallel combination of two MOSFETs, the overall resistance goes down by 2, right? When you have a parallel combination of two resistors which are equal, let's say both of them are 100 ohm resistors. So if you put two of them in parallel, the overall resistance becomes 50 ohms. That's just parallel combination of resistances. Similarly, when you have a parallel combination of MOSFETs, the same thing happens. Why? Because you have two parallel paths for the current. The current can flow through this path from drain to source. The current can also flow through this path, again from drain to source. It's equivalent way of saying that my current can flow through the first resistor or my current can flow through the second resistor as well. So effectively, your current becomes 2 times when you are putting two resistors in parallel, or your resistors becomes half, right? If your voltage is same across the two terminals. If the voltage is same, when you put two resistors in parallel, the effective resistance becomes half, or another way of saying that is that effective current becomes 2 times. Same thing happens when you have transistors in parallel, because transistors are also resistors in a way. So for example, if you are looking into a particular terminal, in this case, let's say you are looking into the drain terminal of these MOSFETs, right? That's what basically this current source is seeing. If you think about this current source, all this current source is seeing is the resistance looking into the drain of these two transistors. Now, if there are two parallel paths, of course, that resistance have been halved, right? Or current has been doubled. Now, what was the equation for current? The equation for current is I equal to K prime over 2 times W over L times V over drive squared. So what I just did is expanded K as K prime times W over L. So if I'm saying that my transistor, the current is getting doubled by putting two transistors in parallel, so effectively what is happening is that the width of the two transistors, of the overall width of the two transistors is getting doubled. Okay. So that is going to be the effect of putting two transistors in parallel. Because my current is going to get doubled, effectively what I can say is that my width is getting doubled. Similarly, when you put two transistors in series, effectively your current is going to get halved, right? Because resistances will come in series, right? Two resistance in series versus if you just had one resistance, your current is going to get halved when you have two resistances in series. So if you put two transistors in series, and that actually may look like this. Let's say you have two NMOS transistors in series. So you have maybe a different gate voltage, and this has a different gate voltage, but the current first flows through the first transistor and then flows through the second transistor. So whatever resistance you'll see for this transistor and whatever resistance that you'll see for this transistor, they will effectively get added. Right? So in that case, if you put two transistors in series, I'll say that my length has become 2 times. So my length, which was L earlier, that will become 2 times of L if I put two transistors in series. Because my current is going to get halved, and that means I can say that my length is getting doubled. And you can imagine the same thing from a resistance perspective as well, right? What is the equation for resistance? Resistance R is equal to rho times L divided by A. So if your resistance is getting doubled, basically your length is getting doubled. If your resistance is getting halved, your area is getting doubled, and area will get doubled if either your width gets doubled, or basically the third dimension, which we generally don't draw in the 2D picture of the MOSFET, that dimension is getting doubled. But that is not there here in the equation. So of course, you have W and L. So if your resistance is getting half, your width is getting doubled. That means your current is getting doubled. And that is synonymous as saying your resistance is getting halved. On the other hand, if your resistance is getting doubled, that is when you put two transistors in series, then your length is getting doubled because your current is getting halved. So it's as simple. Just think from this equation, and it will be very clear that what should happen if you put transistors in parallel versus transistors in series. Okay. So with that, what we establish is that if we put transistors in parallel, then the width is going to get added up. So whatever was the width of the first transistor and the width of the second transistor, they'll get added up effectively. So if you have two of these transistors in parallel on the left side, and on the right side, again, instead of having just one transistor, you put three of these transistors in parallel. So that means if 2x the amount of current is flowing through the left side branch, 3x the amount of current is going to flow through the right side branch. Right? So if the current flowing through one transistor is x, 2x times of current is flowing through the left side branch, so 2x is equal to I1, and 3x amount of current is flowing through the right side branch, so I2 is equal to 3x. So what is I2 in terms of I1? If I1 is 2x and I2 is 3x, I2 is going to be 3 over 2 times I1. So you can also create non-integer ratios. It's not necessary that you have to have integer ratios. You can also create non-integer ratios like this. And then if your technology node allows you to have any width as possible, so this is assuming that the transistors are kind of like a black box. You are not able to change the width or length of the transistor. So you just put transistors in parallel or in series to change the effective width or effective length. The technology might also allow you to have any W possible. That, okay, I'll choose this, the W of this transistor to be 100 nanometer, and I'll choose the W of this transistor to be 110 nanometer. Maybe the technology allows that. And in that case, 100 and 110 will get added, and you'll effectively have a 210 nanometer of width. But if the technology does not allow that, let's say the technology says that you always have to have 100 nanometer width of the transistor because that's what my foundry can fabricate, and the foundry cannot fabricate anything else other than 100 nanometer of width. You can have two of them in parallel and create a 200 nanometer width. You can have three of them in parallel, create a 300 nanometer of width. You can have three of them in series, and if originally the length was also 100 nanometer, then you can have three of them in series and create a 33.3 nanometer effective length. Okay? So all of that can be done, and it's in the designer's control. So as a designer, you're free to do all of that when you're actually doing a chip layout or chip design. All right. So in general, I2 is going to be M over N times of I1. Just from, it's just a general form of what you just learned. Now, to make things a little bit more complex, if you have the lambda parameter, if your lambda is non-zero, so remember that the equation that we had used did not have any lambda. So we just used the first order equation that we had learned, it's basically a second order equation, but I'm calling it it's basically the simple equation that we had learned. But you already know that there is a 1 plus lambda VDS term if you want to take into account the channel length modulation. So if you want to take into account the channel length modulation, then your I or current I becomes K over 2 times V overdrive up squared times 1 plus lambda VDS. That's just the effect of lambda or the channel length modulation parameter. So if you want to take into account the effect of lambda, then you just need to modify that equation accordingly. And if you modify that equation accordingly, what you'll end up with is this, that your I2 over I1, which was just a ratio of W2 over W1 earlier. That was just a ratio of W2 over W1 earlier, but now it will be a ratio of W2 times 1 plus lambda VDS2 divided by W1 times 1 plus lambda VDS1, which is also equal to lambda VGS1. So basically your 1 plus lambda VDS, that parameter will also come in your numerator and denominator for transistor 2 and transistor 1. Okay. So how do we utilize all of this? We just said that you want to replicate a current. Then let's say you have this I1 current. You want to replicate that current multiple times because I might have 3 different current sources in my circuit. So how do I replicate the I1 current? I can mirror it one time. So let's say using this configuration which we just learned, M1 and M2, putting M1 in the diode connected form and then having M2. If M1 and M2 have equal W over Ls, then I2, this current is going to be equal to the current I1. Right? The currents in the 2 branches are going to be equal. Yes. Right. So it depends on what your this current. So if we go back to the previous one, that's a very good question. So let's think through that one time. So what this says is that the current of this structure is going to be determined. So basically this is the current, and wherever this current goes in, let's say you have 2 transistors in parallel or 3 transistors in series, accordingly that will go in here. And then on this side, because you are only interested in the VGS2 and VGS1, effectively the VGS of these 2 transistors, the M2 transistor and the M1 transistor, and from there you are equating VGS2 and VGS1, and then deriving all these equations to eventually figure out that I2 over I1 is equal to W2 over W1, right? So it does not matter what else is connected here. You can connect whatever you want. You can connect a large resistor, you can connect a capacitor, a capacitor will block DC anyway, but let's say you can connect an inductor, you can connect other MOSFETs. But what it matters is that whatever current will flow through this transistor, the same current will flow through that transistor as well. Because the gate of this, the VGS of these 2 transistors are equal. That makes sure that the current through these 2 transistors are equal. Right? So if you say that, oh, I connected another transistor in series on top, and that effectively changes the overall resistance looked into this path, that is true. That overall resistance looked or seen by the VDD is changing. And if you change the W over L ratio of the top transistor, the overall resistance seen by VDD will change. However, this is the beauty of it, that the current does not depend on the resistance. Now it becomes an exact copy of the left side current. Irrespective of the resistance that you have, the current becomes a copy of the left side. So it becomes an actual current source. Remember, the current source has to supply the same amount of current irrespective of what load it is driving. An ideal current source drives the same amount of current irrespective of the load. That's exactly what is happening here, that the current through M1 has to be same as current through M2. Now current through M1 is equal to I1, so current through M2 has to be equal to I1. That means that the current through the top transistor, whatever transistor or whatever resistor I connect at the top, the current through that also has to be same. Question?
Because the current that
Yeah.
means that the MOSFET on top of it, that will its currents to be equal?
So if you try to force 2 currents, yes, it can happen. But remember that currents will be forced only if you have a current source.
Yeah, have that.
So if you try to create another current source, you will force that current, yes. Right.
Those they don't have back.
Can you repeat the question? So this is, your question is related to this circuit, right? That you are saying that, okay, this is my current on the left side branch that is forcing my current through the M2 to be equal to I2. Then exactly. That's you got it perfectly. Because it's KCL. right? KCL has to be satisfied all the time. So the current through M2 is equal to I1 if the W over L ratios are equal for the two transistors. But then the exact same current has to flow through M3 because you have to satisfy KCL. Current has nowhere else to go. If the current is coming in through the source node of M3, it has to pass through the drain node of M3 and then has to pass through the drain of M2 and then through the source of M2. There is nowhere else to go for
If
it.
M3 didn't have that diode,
Yeah, still it would have been true. So let's say M3 does not have this diode connection, okay, and all of that is not present. The only thing is that somehow you make sure that M3 is in saturation. So let's say you bias the gate of M3 in a way that you make sure that the M3 is on and in saturation.
not saturation, then M3 would function like a be open.
Mm-hmm. Yeah. But generally, you would want in analog circuit, you would want your all the transistor to be in saturation so that you can apply only one formula. Current is equal to K over 2 times V over delta square. You can have that transistor in triode and apply the second formula for that to figure out what's happening. But you can make your life simpler by just applying one formula, okay? And make sure that the transistor is in saturation. So the current through M3 is forced by the current through M2. So it's as if that, let me draw it separately on the right-hand side, that you have this M3 transistor, and then you have this diode connected, let's say, and that diode connection, why that diode connection is used, we'll come to that in a minute. But it's as if there is a current source below, and that is forcing the current here so that the current through the M3 is also same as that current. So this transistor actually becomes this current source over here. And that current source is equal to the I1 current if the W over L ratios of M1 and M2 are equal. Now, why do you have this diode connected for the M3 transistor? Because see, on the right-hand side, you are copying that current again and again through M4, M5, and so on. So I can have 10 different transistors on the right-hand side, and then I4, I5, I6, I7, I8, so on. Everything will be equal to I1 if the W over L ratio of all the transistors are equal. Okay. So from one current source I1, I can effectively create hundreds of current sources. So if your circuit needs 100 current sources and your lab does not have 100 current sources, you can create those 100 current sources in the circuit itself. Okay. Yes.
Does I4 become
No, because KCL, I4 is forced. Whatever you connect here, it does not matter. It could be a black box. Whatever you connect here, as long as that is on, that transistor needs to be on, but as long as that is true, this current is being forced. This current has nowhere else to go. I mean, if you want to do it, you can do it. It doesn't matter whatever circuit. It doesn't need to be. Right? You can connect any other circuit here. If you want to connect that gate to this gate, you can do it. I don't know what that will do to the circuit. You have to analyze and figure out. But you can have 100 transistors here. You do not need to have one transistor. You can also have 100 transistors here. That's why I have drawn a black box. But what we are ensuring is that the current going into that black box is forced. The current is equal to I1. I don't care what that black box has. All I wanted to know is that can I copy this I1 current and copy it 100 times? And I am able to do that through this. Okay. So just ensure that the transistors are in saturation so that the way we analyzed it was using the saturation equation, right? We made sure that the M2 transistor and M1 transistor both are in saturation. So that's why we use the saturation equation for both of them. And then we figured out that yes, I2 and I1 will indeed be related with the W over L ratios or the ratios of the width of the transistors. All right. So that's just for large signal or for DC. Till now, we did not talk about any AC signal, right? So we just talked about a DC current source and how to copy a DC current source. You could have also had a small AC signal along with the DC. Let's say I superimpose an AC signal on top of the DC. Okay. And what will happen in that case, the analysis is shown here. I'll go through a little bit of it, the important portion, but I'll leave the entire analysis kind of like a homework, right? A non-graded homework. But what you can already understand intuitively is that if this is a DC current plus an AC current, that AC current is also going to be copied. Right? There's no reason that the AC current will not be copied. So if this is a 1x transistor, and by 1x I mean that the width is 1 unit width, right? X could be in a particular unit, let's say. And M2 transistor is a 10x transistor, that is the width is 10 times larger. That means that the DC current flowing as I2 will be 10 times that of I1. But also at the same time, if there is a AC current superimposed on top of I1, that AC current is also going to be amplified 10 times. So this can also work as a current amplifier. Right? Not only does it work as a current copier or a DC current multiplier, the same circuit works as a DC current multiplier as well as an AC current multiplier. Now, how do we analyze this? Of course, we draw the AC small signal model. That you draw the AC small signal model for, let's just first concentrate on the left side transistor. Okay, the left side branch, where you have a current source. And this is an AC current source right now. So you know that when you do AC analysis, you kind of neglect the DC, right? Because DC and AC, you can think of it as two different analyses which are superimposed on top of each other. So when you're doing AC analysis, you don't need to consider the DC quantities at all. That's why we connect our VDD to ground, because our VDD is an AC ground. That's why you get rid of any kind of DC voltages or DC currents in the circuit. And when you are doing DC analysis, again, you can get rid of all the AC quantities, because if you're doing a DC analysis, AC does not matter. Eventually, the circuit is a combination of both the AC and DC. So they are superimposed on top of each other, but you can, the beauty of the superposition principle is that you can analyze the current sources or voltage sources separately. So your DC analysis could be separate from your AC analysis, just to make your life simpler, but both of them happen at the same time and occur at the same time, even though you can analyze them separately. So if you want to analyze just the AC current, okay, so let's say I have a current source, AC current source, going to the drain and get this diode connected transistor, which is on the left side of the current mirror. So let me draw the current mirror circuit over here, that you have a diode connection here, you have a current source coming from top, and then you have another transistor on the right side. So basically, whatever current is here, let's say this is I1, I will be forcing a current I2, which is a function of I1. So the current I2 will be a function of I1. And if the width or the lengths are equal, then I2 will be equal to I1. So first thing we want to find out is that, let's say we do a small signal analysis of the left side transistor only. So you have the current source, and then you have this diode connected transistor, okay? So for the diode connected transistor, your drain and gate are connected together. So I'm applying my IX. I'm applying my IX on the drain and gate at the same time. So if this is my small signal circuit model, I'll connect my gate and the drain together. So this connection is generally not there in the MOSFET, right? Drain and gate are not connected together. But because this is diode connected and physically you are connecting the drain and the gate, you will be connecting the drain and the gate terminal of the MOSFET together through this wire. And that is where you are applying your IX. Now, you can do the analysis with RO as well, and that will just increase the complexity. But in general, what I want to say here is that if I just have, let's say, GMVGS, let's say I just have the GMVGS as my model of the transistor, and RO is, let's say, infinite. I have lambda could be, let's just assume lambda is 0, and because of that, your RO is infinite, which is 1 upon lambda ID. Now, this current IX, this current comes in And because drain and gate are connected, as this current comes in, gets connected at the gate terminal, that same current flows at the drain terminal and flows through this GM-VGS, goes to ground. If you consider RO, then the current gets divided into two parts. One is GM-VGS and one goes through RO. And because RO is 1 upon GO, you can always model that total IX as GM-VGS plus GO times VGS. And if you don't want to consider RO, then this second term is just not there. Okay. So as simple as that. So what is going to be your Rin? Your Rin is Vx over Ix. What is Vx? Vx is the voltage that gets developed at the top terminal of the current source over here. Right? That's the test current. You had a test current source, and then according to the test current source, you had developed a voltage. You could have also applied a test voltage source Vx and find out what is the current going out of it. You will get to the same analysis. So Rin is equal to Vx over Ix. Now Vx is equal to VGS because you're applying it to the drain as well as at the gate, and source is grounded. So Vx is equal to VGS. And Ix is equal to GM-VGS plus this second term. And if we ignore that second term, then what you're left with is just 1 upon GM. So this is a very interesting conclusion, once again, that if you have a diode connected transistor, if you have a diode, let's say, I have a transistor. Till now, what we knew is that if we are looking into the drain terminal, we see a resistance of RO, and RO could be infinite. If you're looking into the source terminal, the resistance looking into the source terminal is 1 upon GM. Those are the two things that we had proved earlier. The analysis that we did right now is the AC analysis for the input resistance for the diode connected transistor, which we did not do before. So if you are doing the diode connected transistor, in that case, instead of RO, even if you are looking at the drain terminal, you'll be seeing a resistance of 1 upon GM. So when we are talking about the scenario that when you look into the drain terminal of a transistor, you see RO, and when you look into the source terminal of the transistor, you see 1 upon GM. I said that there is one exception of that rule, and this is that one exception. That when you are looking at the drain of the transistor, if the transistor is diode connected, you'll see 1 upon GM and you'll not see RO. And again, you can just do the small signal analysis yourself one time just to get convinced that why it is 1 upon GM and not RO. So if you have a transistor which is diode connected, and then if you have transistor which is non-diode connected, then looking at the drain terminal and looking at the source terminal, in both cases for the diode connected transistor, you see 1 upon GM, as well as looking into the drain terminal, as well as looking into the source terminal. In the non-diode connected scenario, looking into the drain terminal, you see RO, and looking into the source terminal, you'll see 1 upon GM. So this is the table that will be used in all the different circuits that you will see in this course. That only if it is diode connected, you'll see 1 upon GM, both looking into the drain as well as the source. If it is not diode connected, you'll just see RO looking into the drain and 1 upon GM looking into the source. And how do we do that analysis? How do we prove it? Just do a Thevenin equivalent analysis. Just find out the Thevenin equivalent resistance looking into the particular terminal that we are interested in. That's what we did over here. Okay. Now, we can do the same small signal analysis for the second transistor, and eventually you'll find out that the current gain, which is I2 over I1, the current flowing through the second branch divided by the current flowing through the first branch, will again be a ratio of the widths of the two transistors, also a ratio of the GMs of the two transistors. And because GM equal to K times V of V, it's basically the ratio of the two Ks, right? So K2 over K1. So GM2 over GM1 is equal to K2 times V over V2 divided by K1 times V over V1. Now V overdrives are equal, So this is equal to K2 over K1, and K2 equal to K2 prime times W over L, and K1 equal to K1 prime times W over L. So eventually it boils down to W2 over W1 once again. So I'm not going through the AC small signal analysis. I'll leave that up to you. But it's the same analysis that we have done time and again in the course. All right. So what could be some applications of the current sources, right? So we just saw that, yeah, you can have a current source. So one application is that you can use MOSFETs as resistors, right? And you can use MOSFETs as current source. You can use MOSFETs as capacitors and so on. So for example, when we talked about source follower, how does the source follower looks like? That you apply your input at the gate, and you have some kind of a resistance here, and you see your output at the source, right? So this is how the source follower looks like. Now, then in the homework problem 6, we saw that we can replace this resistance with a current source because the current source has infinite resistance. The gain in this case is going to be GMRS divided by 1 plus GMRS. Again, something that we had proved earlier, so I'll not go through the proof once again, where RS is the value of this source resistance and GM is the GM of the transistor. The voltage gain AV for this particular source follower configuration is GMRS divided by 1 plus GMRS. Now, if this RS is a current source, and current source has infinite impedance, as we already know, then voltage gain, which is GMRS divided by 1 plus GMRS, you can divide the numerator and denominator both with RS, and because RS is infinity, you'll eventually see that the voltage gain will be almost equal to 1. If RS is infinitely large, that is if RS is a current source. Now, that is if RS is actually an ideal current source. We have already learned that how to build a current source using transistors. So you can build that current source using transistor. It's basically this current mirrored circuit that you originally had this reference input current. You mirrored that current over here. So this transistor M2 effectively becomes a current source at the source of the transistor M1. And if you're applying the input voltage Vin at the gate of the transistor, looking at the AC output voltage Vo at the source of the transistor, that's basically a source follower. And then the equation for the source follower is GMRS divided by 1 plus GMRS. What is RS in this case? What is RS in this case? RS will be the resistance that you see looking down from the source terminal of M1, right? RS is the resistance that you see looking down from the source terminal of transistor M1. And that is this RS resistance. What is the resistance that you'll see looking down on the source terminal at the source terminal of M1? You'll see the drain terminal of M2, and M2 is not diode connected. M1 is diode connected, yes, sure. So looking into the drain of M1, not M1, M3 is diode connected. So looking into the drain of M3, you'll see 1 upon GM3. But looking into the drain of M2, you'll see RO2. Right? So you'll see this RO2 resistance looking into the drain of M2. So your gain, AV, is going to be equal to, I'll write that down over here. Your gain is going to be equal to GM1 times RO2 divided by 1 plus GM1 times RO2. Now, of course, if lambda of M2 is 0, then RO2 of M2 is going to be infinite. If RO2 of M2 is going to be infinite, this voltage gain will be almost equal to 1. And that's the job of source follower anyway. You can also divide the numerator and denominator with GM1 RO2. That's what this equation shows over here, which is also almost equal to 1. So you saw an application of the current source that it can be used as the load. So RS was a load resistance, right? Why do we call it the load resistance? Because your output was observed across that resistance. So this was the load resistance or the output resistance. Now, instead of using an actual resistance, which is generally much larger area consumption in a IC. So this might not be very clear at this point, but generally a resistor or a capacitor in an IC technology, within an IC, the resistor or the capacitor takes a lot of area. Whereas MOSFET can be very small. You know that MOSFETs can be scaled to nanometers. People are talking about single digit nanometer or going beyond 1 nanometer as well these days, right? So MOSFETs can be very, very small. So you can implement a very large resistance, ideally infinite resistance, just with one MOSFET. So if you want to save area on your chip, and in your chip, the area is the real estate. Because if you have more area available, you can pack in more and more transistors. That means you can have more and more features or more and more functionality. So that's always better in a chip. You want your phone to be a better phone in the next version, right? So you want to have more and more functionality. That means within the same area, you need to pack in more. So if you can replace your resistors or capacitors with transistors, that's always a good thing. So what we did here is that replace that RS resistance with a transistor having a very high RS or having a very high effective resistance looking down on the drain terminal. So instead of using a real resistor, now you have a completely MOSFET-based circuit achieving the same thing, maybe even in a better way, because RS would have been like you would need an infinite RS, and in this case you can get it if the lambda of the transistor is very close to the zero. All right, any questions here? If not, I would like to start summarizing what we learned in terms of MOSFET-based amplifiers. And this is the MOSFET cheat sheet that I have already posted on Canvas. So there's the MOSFET cheat sheet that I had already posted on Canvas. And I'll discuss this today as well as in Friday's lecture. And this is just a summary of whatever we have learned, right? So the first thing that we learned was the common source amplifier. That why would you call it common source? Because your source is the reference terminal or which is grounded. Your input is at the gate, your output is at the drain. Then you call it the common source. MOSFET has 3 terminals. One is reference or common. Input is one other terminal, output is the third terminal. The small signal model for this will look like that this is the transistor over here. And you can consider the RO. In that case, the RO will come in parallel to this. But in most problems that we'll consider in this course, we'll just assume that RO is infinitely large. So what you have here is just the RD connected between the Vout and the AC ground, which is your VDD over here. So you basically have RO in parallel with RD, but if RO is infinitely large, you have just RD. The voltage gain will be of the form GM times R out. And in this case, it will be minus GM times R out because of the direction of the current flow. The current flow is in this direction. This is ground. So your V out has to be a negative quantity, right? Because otherwise current cannot flow from ground to V out. And on the other hand, that basically in terms of AC, what that really means is just that there is a 180-degree phase shift between your input and output, because minus is just a 180-degree phase shift in the signal. So our job is to find out what is the effective GM in the circuit and what is the effective R out in the circuit, and multiply the two, you'll get your AV. When RO is tending towards infinity, capital GM is equal to small gm, R out is equal to RD. When RO is not infinity, capital GM is still equal to small gm, R out is RO in parallel with RD. So if you cannot ignore RD, or if you cannot ignore RO, your R out just becomes a parallel combination of RO and RD, right? And if you can ignore RO, that is when RO is infinitely large, then R out is just RD. How do you find out capital GM? First step is that you get rid of RD. Again, basically finding out the Thevenin, or in this case, the Norton equivalent current, right? So if you have a black box with a load, if you want to find out the GM, what would you do? You'll apply some input voltage and you'll find out what is the output current. The ratio of output current to input voltage will give you GM. So how would you find out output current? Because you are interested in the output current, you are basically interested in the Norton equivalent circuit. In the Thevenin equivalent circuit, you are interested in voltages. In the Norton equivalent circuit, you are interested in currents. So how do you draw the Norton equivalent circuit? Is that you short the load. So first start by shorting the load, which is shorting the RD. Find out what is your I out as a function of V in. Your GM is going to be I out divided by V in. So that is the method to find out GM. And again, nothing new here. It's just what you learned in 3111. Method to find out R out. So you'll try to find out what is the resistance looking into the output terminal of the black box. In that case, you want to open RD and short any independent voltage sources. Then put a voltage source Vx at the output. Find out the Ix current coming out of the output voltage source. And then the R out in the no load condition will be Vx divided by Ix. And the overall R out, when you connect back the load, will be the R out that you found in the previous step in parallel with RD, because you had gotten rid of RD in the first step. So again, nothing new here. It's same as what you learned in Thevenin and Norton. But I just wanted to make sure that I list it down in a way that you can use it in the summary sheet. We'll stop here. In the next lecture, we'll just continue with all the discussions. But again, it's just a repetition of what we had learned.
I was wondering the whole class, I was like,
Right.
okay, so again, I'm getting how these MOSFETs are working. I wonder like where they put all of these like RD resistors and RS resistors when they
Right.
make large logic circuits.
Right.
And then you went, oh, they don't use them. They
Right.
just use the transistor.
Right, exactly. So you can use the transistor as a resistor, right? So
I mean, it's kind of silly though. But, oh, how they do it.
no, of course. I mean, it's not silly, but yeah, I mean, it's so when I learned it for the first time, I also thought the same thing that, oh, that's an interesting concept. Why didn't I mean, I'm learning about MOSFETs, but why didn't I think of that? Right. So
Yeah, using
you
it.
kind of have that kind of a moment, right? That yeah, you know that the resistance of the like the resistance looking with the source is on upon GM. So by controlling the GM, you can actually put a transistor in a way that you look into the source of the transistor, and that gives you a variable resistance.
Yeah, and then you
Right.
can use that resistance to set other transistors.
Exactly. So that's what they do in a real circuit, because they don't like to use resistors because resistors are bulky. They're very big as compared to the transistor.
As far as resistors tend to like be that big, where
Mhm.
transistors can be like really small.
Right.
Huh. Okay. Thank you.
Yeah.